Good morning, everyone. It's really a privilege to be here. My name is Stella Kafka. I'm the Executive Director and CEO of the American Meteorological Society. And I think I'm really jealous of those who have met Dr. Mahoney in person. This lecture series was established to honor his contribution to the field and continue his work of bridging scientific understanding with policymaking. And I'm not going to tell you more about his life and work because Dr. Carlis has already introduced him in a very eloquent way. But I want to emphasize that this lecture series celebrates the legacy of an exceptional individual who has been an inspiration for many. I haven't had the privilege of meeting him in person. So on behalf of the AMS, I would like to invite to the podium our president, Dr. Anjali Banzai, who will share some personal anecdotes and introduce this year's lecturer and lecturer.
Good morning, everyone. Welcome to the annual Dr. James Mahoney Memorial Lecture. I'd like to extend a special welcome to Dr. Mahoney's family, Taya, his wife, who is joining us remotely, son Jim and wife Jane, who are with us in person, and several members of the extended family who are joining us remotely. We are so fortunate to have had the likes of Dr. Mahoney in our field. He served as AMS president during the course of his distinguished career as an academic, a scientist, a business executive, and a director of key US government environmental programs spanning 5 decades. Phew. You know, the AMS Washington Forum is all about bringing together these 3 key stakeholders. And I was thinking this morning, Jim actually had spent his life in all those 3 sectors, private, academia, and government. He actually exemplifies the best and serves as a role model for those of us who follow. After earning a doctorate in meteorology and geophysical fluid dynamics at MIT, he was associate professor of applied meteorology in the School of Public Health at Harvard. Later, he co-founded Environmental Research and Technology, one of the earliest environmental engineering and services companies. He was director of Bechtel's Global Environmental Industries Business Group. Under the Reagan and Bush senior administrations, he was director of the National Acid Precipitation Assessment Program, also known as NAPAP. Some 2 decades ago, as Dana mentioned, in the Bush Jr. administration, he rejoined the government as Deputy Administrator of the National Oceanic and Atmospheric Administration, NOAA. Our hosts here were sitting in their auditorium here. At that time, he was also our fearless leader at the US Climate Change Science Program. That is when I first met Dr. Mahoney. He held meetings in his grand office in Main Commerce Building. He made it a point to get us know his staff, and I was actually at DOE at the time, on a first name basis. We all have our favorite Dr. Mahoney anecdotes, and I have some too, but I won't take up more time. We are here to hear Dr. Busalacchi on the topic of the future of forecasts, Earth system prediction in the 21st century. So to Tony is president of the University Corporation of Atmospheric Research, aka UCAR. He has had a distinguished career in Earth system science. Prior to joining UCAR, he has held several leadership positions in government, academia, and business. I guess UCAR can be considered a corporation of some sort. He was at NASA. He was the chief laboratory at the Laboratory for Hydrospheric Processes at Goddard. He was the director of the ESIC, the Earth System Science Interdisciplinary Center at the University of College Park, Maryland, right here, this campus. He was chair of the BASC at the National Academy of Sciences. He was on the Joint Scientific Committee at the World Climate Research Program. The list goes on. Again, in the interest of time, I won't elaborate further. Welcome, Tony. So glad you are here to deliver the annual Dr. James R. Mahoney Memorial Lecture.
Thank you, Anjali, Stella, and Danae. When Anjali reached out with the invitation to give this lecture, I was really touched and honored and humbled. It really is a special treat for me to give this lecture, first here at M Square, and that when I was the director of ESSEC Next Door, my dean, Steve Halpern, and I were collaborating with Jim once he retired from NOAA, and our collaboration was on the topic of climate information responding to user needs. And so Jim was a dinner guest at our house in Burtonsville. Steve and I traveled to Jim's house, working across the kitchen table at their house in Virginia. So again, very fond memories of working with Jim. The other comment I'm going to make, if Anjali will allow me, in last month's BAMS, there's a little introduction about Anjali's presidency. I'm going to quote from the article, and Anjali says, "We now know that the atmosphere is just one very important component of the Earth system, interacting with the ocean, the land, ecosystems, geology, and human systems. Understanding and responding to the system on a host of spatial and temporal scales is the grand challenge of our times. That's the theme of the 2025 AMS annual meeting in New Orleans. My theme is titled, Toward a Thriving Planet, Charting the Course across scales. So local, regional, and global scales, from weather, hydrology to climate. The state of Louisiana and the Gulf region are confronting problems such as the loss of wetlands. So hopefully we will consider those issues a bit, engaging with the local community." So Anjali, thanks for writing the abstract for my talk today. You said it better than I could. So what I'm going to do over the next 40 minutes, 35 minutes, is peer into the crystal ball, not for tomorrow, but for the decades ahead. And if I can get this moving, there we go. And the vision is listed up here. And I would argue that we are on a threshold in a new era of prediction. A better understanding of the entire Earth system is going to transform our prediction capabilities to a whole range of societal benefit areas. At NCAR, we're pushing out in these areas, but to make advances here, we need enhanced observations, Earth system models, supercomputing resources, the data analytics to take advantage of all that information. And accomplishing this, as already said in the outset, is going to require partnerships among the government, the private sector, and academia. So the importance of a good weather forecast really became clear during World War II. At that time, forecasting was still relatively primitive. We didn't really have numerical weather prediction models. We had limited observations of the atmosphere, but weather forecasting was essential to the D-Day invasion. And what you're looking at here is the hand-drawn weather forecast map that was used to plan the D-Day invasion. Now, after World War II, the United States made significant investments in forecasting, and I would argue an unprecedented investment in forecasting. And this led to the first numerical prediction models that were run on the ENIAC computer of its day, pictured here at Princeton in 1950. Now, with this new focus on furthering the science of meteorology came the realization that there was a need for a national hub to coordinate and accelerate efforts. And that led to the formation of NCAR. You can see the building here, the construction of the iconic Mesa Lab designed by I.M. Pei in 1960. So post-World War II, with our knowledge of the physics and dynamics of the atmosphere, the advent of digital computing, this ushered in a whole new era of numerical weather prediction, to the point now in this country, we have a multi-billion-dollar private sector weather enterprise that is the envy of the world. And I would submit that we are now at a similar juncture today that we were back in the 1950s with our ability to predict how the Earth works as a coupled system. Now, in the decades that followed, numerical weather predictions continued to improve and become more sophisticated. We began to understand that to improve predictions further, we needed to expand our horizons beyond just the atmosphere. And this new way of thinking, this new perspective was enabled by the era of satellite observations. And that perspective from space really allowed us to have a greater appreciation for the Earth as a coupled system. And so NASA in this country, NOAA, the EU with its Sentinel program, and an ever-increasing number of spacefaring nations, we now have and enjoy a whole fleet of satellites in orbit observing the planet. And again, it's that perspective that allows us to piece together the intricacies of how the Earth operates as a coupled system. So you may hear Richard Strauss in the background and the theme for 2001 Space Odyssey, but it does bring us to today, where I would argue that we are standing at the dawn of a new era, where if we have the investment on the scale of that after World War II, we could vastly improve the prediction of the entire Earth system. And so what's illustrated here is, what do I mean by Earth system prediction? At its core, the kernel is of the physical climate system, the atmosphere coupled to the ocean, to the land surface, to the cryosphere. And then how that physical climate system interacts with chemistry and biology, inclusive of marine and terrestrial ecosystems. And then how that coupled physical natural system impacts humanity and is in return impacted by humanity. Now, we're not talking about prediction for prediction's sake as some sort of ivory tower esoteric exercise. The ability to accurately predict the entire Earth system across a whole range of societal impacts is going to have tremendous impacts to society, be it forest, riparian zones, agriculture, the built environment, disease vectors, etc. And so what does Earth system prediction really look like? Talking about prediction that is seamless across multiple disciplines, literally stretching from the sun to the bottom of the sea and everything in between. In the past, our communities were kind of on separate tracks. We had NWP, we had climate variability, and ENSO, we had climate change. But clearly, we know how ENSO affects hurricanes in the Atlantic and what might be coming this year with a La Nina on tap. Climate change, also we're seeing the effects of climate change on severe storms. It also means being seamless in scale, including predictions that go from the global scale to the regional scale to the local scale, down to the scales in which the decisions are being made. And lastly, it means seamless across the scale of processes, from the micro scale to the macro scale. For example, cloud condensation nuclei, all the way up to ocean currents that sweep across the full breadth of ocean basins. And so, as Angeli said, I believe this really is the grandest of all the grand challenges for Earth and environmental science. It's trite to say, we do only have one planet we live on, and I think we owe it to ourselves to exploit this nascent predictive capability. And we're already starting to see some tantalizing and intriguing possibilities for the future. And I think over the decades to come, we're going to see an exponential explosion in forecasting, whereby a richer understanding of how the Earth operates as a coupled system will allow us to better predict that system far beyond just the physical climate system, from renewable energy production, harmful algal blooms, threats to fish stocks, crops, oceanic dead zones, vector-borne diseases. And yet, even with a perfect understanding of the connections of the Earth system, our prediction ability is going to be hindered because we're dealing with a nonlinear, chaotic system. And so at this point, we don't really appreciate what are the limits to predictability of this system. For example, some recent work at NCAR demonstrated that we may not know when the Arctic is ice-free to plus or minus a decade or so. Now, Earth system prediction is also a matter of national and global security. A lot on the news over the past weekend or so about solar storms, but in 1967, a solar storm jammed radar and radio communications over the northern tier of North America. And at that time, we were kind of blind to what was going on. We initially attributed that to the Russians, and it almost brought our two countries to the brink of war at that time. And so the ability to better predict space weather is a key point, as stressed over the last several days. What we're looking at here is a video from NASA showing a coronal mass ejection episode striking planet Earth. And yet, if we were in the Carrington event of 1859, at that time, telegraph wires were literally on fire. If we had a Carrington event today, it literally would cause a meltdown of our telecommunication system across the world. So what we saw during COVID is on the timescale of months, the world economic system was brought to its knees. If we had a CME of the scale of the Carrington event, it would bring the world economy to its knees in a matter of days. Now, the term climate change as a threat multiplier was coined by Sherry Goodman, a colleague of mine. She used to be on the UCAR board of trustees. And she and I were members of a study at the National Academies that was sponsored by the intelligence community, looking at the impact of climate change on political and social stressors overseas. What's shown here is the floods in Pakistan of 2022, not of this past few months, but in 2022, over 1,700 Pakistanis were killed by those floods. And unfortunately, that's a reminder of what happened in New Orleans. So those that know me, the frame around my license plate on my car says August 29, 2005, never forget New Orleans, when at that time, more than 1,700 citizens in New Orleans lost their lives. And so the AMS meeting in New Orleans this year, next year, will be 2025. That will be the 20th anniversary, so to speak, of the impact of Katrina. Now, in this study, that was an unclassified study, one of the areas we focused on was Pakistan, but the flip side, the drought conditions in Pakistan, where there's tremendous contention for water resources. So during times of drought, the nation needs to decide whether or not water resources are diverted to rural areas for agriculture or diverted into the cities for industrial and power generation. And when the decision is made to divert power to rural areas, there are tremendous brownouts in the major metropolitan areas of Pakistan, such as Karachi. We don't hear that in the West, causes a considerable amount of civil unrest. And of course, this is the country that has the bomb. Earth system prediction is also very important to our armed forces. I also had the good pleasure of co-chairing a study that was commissioned by the Chief of Naval Operations. And I had really the good fortune of serving as co-chair together. The other co-chair of the study was Admiral Skip Bowman. And of all the armed forces, I would say the US Navy is the most enlightened with respect to climate change because of their forward presence around the world. Something on the order of $100 billion of US naval assets are vulnerable to a 1 meter rise of sea level. We're aware of Russia planting a titanium flag at the bottom of the Arctic Ocean. So the Arctic is a region of cooperation, competition, albeit low conflict. And so we need to better predict when the Arctic is going to be ice-free, allowing greater access for several nations, and again, the possibility of conflict when we're concentrated in such an area. So to move beyond this vision, we need to radically expand investment. And I argue this is basically a grand challenge on par with the Human Genome Project. And again, this is going to require substantial investments as well as cooperation across agencies, scientists from different countries and disciplines. And yes, we are in an era of austere budgets, flat budgets, but that's all the more reason to be thinking about the future. Now is the time to be planning for the future, not when we have largesse. And so this figure sort of illustrates sort of the new paradigm emerging. What we're looking at is the ratio of US R&D to gross domestic product as a function of the private sector in orange and the federal government in blue. And so what you see is post-World War II and the Cold War and the end of the Cold War, that model of federal investment in R&D is not as valid as it used to be. And so this illustrates the need to be working together in new ways. And I saw that firsthand when I was next door at ESSEC. At that time, Neil Jacobs was at Panasonic. He was funding graduate students here at Maryland. And they were using the TAMDAR data. They had access to better computing resources than at NCAR. They were exposed to the rapid turnaround cycle of the private sector. She and he had opportunities for jobs when they graduated, et cetera. So it was a win-win situation. And I'll say a little bit later about our partnership between NCAR and MPAS as another example of sort of emerging private sector activities. And so NCAR, we're moving out in this area. NCAR was formed, as was UCAR, in 1960 when we had 14 founding universities. We now have over 126 universities across the United States and North America. And together, not just NCAR, but our UCAR community programs, since our founding back in 1960, we tried to serve to multiply and amplify that NSF investment in NCAR. And at its core, we still hold to the words of our founder, Walter Roberts, the science that we do is in service to society. Again, very consistent with really exemplified Jim's career in the public and private sector. NCAR is working across a range of disciplines beyond just meteorology as it moved towards Earth system science, climate science, oceanography, hydrology, ecology, biology, geography, and social sciences. And a few examples. NCAR is already breaking new ground. Here is the output from Wharf Hydro. What we're seeing is basically the heartbeat of the nation's river and streams as storms and weather systems pass across the country. Wharf Hydro served as the basis for NOAA's National Water Model at the National Water Center in Tuscaloosa, Alabama. But for an accurate hydrologic prediction, need not just a good weather forecast, you need to know the geography, the soil types, the vegetation, soil moisture of the river basins, transpiration, snowpack, et cetera. So already it's a land atmosphere coupled problem. Wharf Hydro is just one of the many versions of Wharf. What we've shown here is a simulation from Wharf Hydro, a Wharf Fire that combines atmospheric conditions with environmental terrain, fuel loading, again, soil moisture, vegetation cover, feedbacks between small scale, large scale circulation. And this is a visualization of Colorado's East Troublesome Fire in 2020. It was an explosive fire that started on the western slope, jumped over to the eastern slope, and started moving into Rocky Mountain National Park and Estes Park. This is a simulation of the Hall Ranch wildfire in 2011. This is about 6 miles from where I live in Longmont. And this has served as the basis for input for a state of Colorado, a state fire command post that's stationed in Rifle, Colorado, that's predicting these situations, these types of variables on the left. And WRF is also being used to predict how much wind will be used for wind turbines. NCAR's sun forecast system provides actionable prediction of solar energy production. Our major provider of energy in the Mountain West is Xcel Energy. And as a result of having access to this information, it saved the ratepayers in the Mountain West about $50 million over the past 10 years. Another example is heat wave prediction and the importance of oceanic hotspots and oceanic heat waves. And what's shown here is the fingerprint of sea surface temperature in the Pacific Ocean that precedes drought conditions in the continental US by about 7 weeks in advance. And this is an example for 2012. Also on the news, especially in the summertime, is the situation of reservoir levels in the semi-arid Southwest. Drought prediction is taking on ever-increasing importance. A good foundation for that is NIDIS, but then we need to keep pushing the envelope on seasonal prediction of drought situations so that to provide better guidance to officials making decisions on reservoir storage. And shown here is an example of such a seasonal forecast by Andy Prine. And a key variable in these forecasts is the amount of water vapor in the atmosphere starting in April prior to essentially the monsoon system in the region. Talked about sea ice, just a visualization here where work at UCAR has demonstrated the importance of the Atlantic meridional overturning circulation that guides decadal variability of sea ice in the Arctic. And we're also doing work with CDC in the region, looking at the outbreaks of West Nile fever. And the work here has pointed to the importance of summertime temperatures, not precipitation, but summertime temperatures for West Nile outbreak. So against this backdrop of sort of illustrative examples, what do we need to push this science further, eventually making operational Earth system forecasts? First, we need more, better, new observations, cutting edge, high resolution Earth system models, high performance computing resources to bring it all together, data assimilation to bring the models, the observations together, artificial intelligence and machine learning to make more efficient use of the observations, the modeling, and the high performance computing resources. So earlier we spoke about large satellite platforms. We're also seeing a revolution in other observational technology and platforms. With the Internet of Things, we now can provide observations to feed a whole range of tomorrow's Earth system observations. And so the ability for everyday objects to connect to one another and exchange data opens up new possibilities for collecting observations. One of these areas are some of the challenges faced in regions and least developed countries around the world. What we're looking at here is some of the 3D printed weather stations that are being deployed by UCAR in Kenya and Zambia, regions where there's not a lot of infrastructure and capacity, but relatively cheap stations to provide information to the region. And in the future, we're also going to be able to make use of observations embedded and sensors embedded in everyday objects, in homes, in vehicles. And one example is shown here is sensor technology we created that's being used on snowplows to provide real-time observations of winter road conditions. And so, in fact, everything around us these days, I can open up my phone and see what's going on in my refrigerator back home. So from household appliances to cell phones to vehicles, the Internet of Things, again, is going to be providing a service as a platform for new observation types to feed tomorrow's Earth system prediction models. And so speaking of smartphones, smartphones can have sensors that serve as barometers. There's something on, as of 2022, $6 to $7 billion smartphones were estimated worldwide. There's a question of the precision of such observations, but when you're talking about billions of platforms, you can beat down the error by root n quite easily. Now, looking to the future, we are going to be obtaining more observations from small satellites that can be more agile and cost-effective. The path that we're on with satellites the size of a school bus, these Battlestar Galactica platforms, is just not sustainable. And so we need to go to small sats, CubeSats, formation flying, constellation flying. The work we're doing together with NOAA in Taiwan with COSMIC has really revolutionized low-cost efforts to profile the temperature and humidity of the atmosphere via GPS meteorology technology. A whole host of private sector efforts have grown up as a result of that. Drones are other new platforms, from small quadcopters to the global hawk, really have the potential to be more of a game changer, to go to regions that are inaccessible, in the boundary layer regions of the ocean, the atmosphere, land, and the atmosphere. If Domino's wants to deliver your pizza right side up, it needs to know about the turbulence in urban canyons. And so I think we're going to see an explosion of efforts in the built environment with the observations taken from these sorts of platforms. Another data assimilation challenge here to take advantage of those observations and feed them into real-time predictions of turbulence in urban canyons. Drones also apply to the ocean realm, be it floats or gliders. Again, going down 2,000 meters or so, very inaccessible parts of the ocean, but even parts of the ocean even more accessible. Pinnipeds are outfitted with sensors for temperature, oxygen, chlorophyll concentration to go profile underneath the ice sheets. When they emerge back for air, they telemeter their results back to shore. Now, the meteorological community has long recognized the value of having automated, interconnected observation systems like this system for the Midwest. That's Lake Michigan on the right. Something on the order of 36 states now have mesonets. And it's these observational networks that's going to underpin our ability to model going from the global scale down to the local scale across disciplines. And so one of the biggest challenges is to need to model the Earth system at scale with limited high-performance computing capabilities. Right now, the global community is striving to have 1 kilometer global resolution in global circulation models. This is our new model at UCAR, models for predicting across scales, where it has variable mesh that allows you to have high resolution where you need it, let's say over North America, and then lower resolution, let's say out over the oceans where nobody lives. Again, allowing more of a seamless view across scales from the global to the regional. Here is an MPAS run at order 4 kilometers. And I foreshadowed before, the emerging partnership between academia, the research, and private sector. So this is a partnership that we had with IBM, where IBM ported MPAS to GPUs. And that then served as the basis for IBM's graph model. And at the same time, we were able to have benefit from the software engineering efforts at IBM to port the model to GPUs. The same holds in the ocean. What's shown here is a 1/10 of the degree high resolution ocean within the coupled Earth system model at UCAR versus a 1 degree lower resolution simulation at the bottom. And why it's important is illustrated on the next slide. What we're showing here, we're looking at simulations of atmospheric rivers in a coupled climate simulation. The low resolution coupled run is on the right. And with the low resolution coupled model, underestimates atmospheric rivers by about 60% compared to high resolution, primarily because of the better exchange of fluxes of heat and moisture between the atmosphere and the ocean. So to do what we've been discussing, we need ever-increasing high-performance computing resources. Shown here is our 3rd generation supercomputing machine up in Cheyenne, Wyoming. Has a peak performance of about 20 petaflops, which is 4 times faster than its predecessor, Cheyenne. This became operational a year ago with an 80-20 split between CPUs and GPUs. And to enable the sort of vision we've been talking about, we're going to need increases in high-performance computing, at least 50 to 100 times from what I've been talking about. And so when you look at today's observations, the output from today's numerical models, we are talking about a big data challenge. UCAR's Unidata has partnered with NOAA and Amazon Web Services to place the NextRad data into the cloud. And as a result of having those data in the cloud, the access to those data has been made much more easy, and the use of those data has increased 2.5 times as a result of those data being in the cloud. And so going forward, the vast amount of data that we have is going to create, again, more demands for machine learning and data analytics. I recall In 2018 at UCAR, we hosted the AMS Summer Community Meeting. And at that time, in 2018, I stated the day was not too far off in the future where the standard to beat for 24-hour weather forecast was artificial intelligence versus NWP. And I will say I got a certain amount of pushback from members in the audience in 2018. And so I was off on that forecast. I thought it would come sooner than it has, but that day is here. And there's going to be a lot of discussion tomorrow all about AI and ML. But it's not just AI for data mining or prediction, it's also for data assimilation as well. So again, a whole host of opportunities. And this is just a schematic. You're going to go into more detail, just a schematic of GraphCast showing sort of the covariance structures of the GraphCast processor. And the European Center has really jumped out in front in analyzing and setting up an internal AI evaluation and forecasting activity, and shown here the difference between cyclone tracking and atmospheric rivers in terms of GraphCast and the high resolution model at the European Center. So now I'm going to shift gears a bit, and I'm going to focus on the importance of regional Earth system approach. And here I'm going to use the Gulf of Mexico, which is really a microcosm for the Earth system. Last week I was in Venice talking about the potential for doing this in the Mediterranean and for the Venice Lagoon. And I'm going to start with the Deep Horizon disaster in 2010. NOAA's response to the Deep Horizon disaster was truly admirable and remarkable. Every single line organization at NOAA stood up and responded. National Weather Service, NESDIS, OER, National Marine Fisheries, National Ocean Service, all did just a great job. And yet, a priori, there was no way to fund R&D across every single line organization. NOAA, NASA, NSF, universities, my former university here, the reason why ESSEC was formed was to cut across those traditional stovepipes. And so the Gulf of Mexico is an example of a region under the influence of multiple stressors across the physical, natural, and human system. 50% of the world's population lives within 100 kilometers of a coastline. 39% of the US population live in coastal counties. And so this is a region that has these multiple effects shown here. We have very intense tropical storm formation when tropical storms form over warm core loop current eddies. We have dead zones, hypoxic zones as a result of nutrient loading coming down from the Mississippi. We have harmful algal blooms in the region. We have coastal communities where their livelihood waxes and wanes on the price of oil. We have relative sea level rise as a result of the thermal expansion of seawater, and also subsidence caused by the pumping of oil and groundwater within the region. And what this also illustrates is the fact that the control of human impact on the Earth system. And what's shown here is world population versus GDP. You can show the same for greenhouse gases. The two curves are basically follow each other, track each other for the past 2,000 years. And so to fully understand the dynamics of either system, Earth and human systems, they have to be coupled. And so when the human system was small relative to the Earth system, the two could be dealt with separately. And that's kind of how our modeling enterprise has developed over decades. But the human system has now grown to the point that they must now be modeled and coupled together. This is not just for the climate change problem. This is really for subseasonal and longer time scales. So as part of the BP and Transocean settlement from Deep Horizon, the national academies were provided $500 million to give out grants to improve understanding of the region's interconnecting human, environmental, and energy systems, and fostering application of these insights to benefit Gulf communities, ecosystems, and the nation. So for a number of years, I served on the Gulf Advisory Board for the National Academies. And here's a regional Earth system prediction vision for the Gulf of Mexico from season to decades. And this basically follows from the Chesapeake Bay forecasting system that we developed next door at ESSEC by Professors Raghu Murtagudi and Jinzhong Liang. And this is a graphic that Jerry Melillo and I developed. Basically, it's conceptual model of coupling a regional human system module together with a regional Earth system model. And so you could think the top has some similarities to an integrated assessment model, but some other differences. Intelligence community, defense community has human-based, agent-based models. And so the time has come to, it's not an easy task to model human beings, but we need to start building into our models the ability of humankind on the system and the feedbacks. And so much like evaluating the trade space when in the satellite program, we're talking about a system that you could do query-based scenario probing the scenario space. You can't do this at the global scale. This is the sort of thing you just can't do yet. And so regional Earth system models can serve as a test bed for what can go and what data we need to drive something at the global scale. But you can simulate future scenarios, model single and multiple threat scenarios, probe a range of mitigation and adaptation scenarios, inclusive of infrastructure. And so it needs to be data-driven. So in the case of the Chesapeake Bay forecast system, we're applying fertilizer at the county scale to look at what the downstream impacts were for Chesapeake Bay. We could do if-then scenarios if we had changes from crop types or more move from crops to impervious surfaces. And then again, to guide policy decisions and look at disaster responses. Probe the system for where would you want to pre-stage supplies in response to humanitarian assistance and disaster relief. So to wrap things up, I would submit that this challenge and the opportunity it presents will lead to an entirely new Earth system prediction enterprise. This is much like we saw with the growth of the private sector for the weather enterprise, somewhat belatedly for climate services. But in the decades ahead, this is not just tomorrow, I am talking the decades ahead, I anticipate, what we saw for the multi-billion-dollar weather enterprise is going to be dwarfed by what we see in terms of Earth system prediction. And so much like medical research, where we have sophisticated tools and techniques to analyze the human body, we can foresee the opportunity to better diagnose and predict the health of our planet. And so I would argue that the European Union is leading the way with its Earth system services via the Copernicus Copernicus program, where it brings together the atmosphere, emergency management, the marine sector, land, climate change, security, brings together the observations, the models, and the services, be it harmful algal blooms, prediction of sargassum mats and where they're located, to a prediction of marine heat wave forecasts. But again, to make such a vision a reality is going to require this cooperation across academia, business, and the private sector. And in closing, I would say that if we exercise the will to make Earth system prediction a priority, we have the ability to avoid some of the disastrous impacts we've experienced in the past, as illustrated here. So in conclusion, thanks very much for your attention. As you can see, I'm quite upbeat about the prospects for the future. And for me, it's quite exciting to be in this field at this point in our history. So thanks very much.
Thank you, Tony, for that talk. I think I was just thinking as I was hearing you, Jim would have been proud at where we've gotten, over the past couple of decades. States, and so hopefully he's watching over us and enjoying the treat. Stella, can you hear the question from the YouTube? Okay, if there are questions, we welcome them at this point. You come up and say who you are and ask.
Or just shout it out. I'll repeat.
Okay, Tony, I'll start the ball rolling.
Thanks.
As always, thank you so much for your great comments on the what and the how. And especially right at the very end, you started getting into the why.
Yep.
And I was heartened to see that. And I was also heartened to see an article that was in this morning's Washington Post. And the title of the article is "Tornado Season Has Been Busy, but the death toll is relatively low. Why?" And if you read through that article, it kind of brings together all the stuff that we're trying to do and what the outcome is for the general public because of what we're doing. So I'm heartened by this information as always. That's why I keep coming back to these things and just glad to hear what's going on, especially with the current programs and some involved with things over there a little bit too. So thank you.
You know, and thanks for the comment. And also, I will say, being here, you know, near the university, I was at ESSEC for 2000 to 2016. And I would say in about 2010, I saw a difference in the students that were coming in, and more of the students were really keen on doing research that mattered to what's up here, improving the quality of life for society, and doing double majors in public policy and meteorology and oceanography, or communications and science. And I think there is a sea change there in academia where our students really want to make more of a difference than in the past. Yep, thank you for that.
Maybe I'll ask a question. Yeah. So for the AMS, I mean, there seems so much to be done, right? Versus science. So given the AMS brings together, you know, three main sectors, how do you think the AMS should map its future so that we optimize our service to society, optimize the research, optimize the private,
So I'm gonna answer it again from the lens of my experience here, and that is, I think in academia we need to do a better job of preparing our students for jobs in the private sector. Not everybody needs to look like their major professor, needs to have a PhD. There's a heck of a lot of gainful employment with just a bachelor's and a master's degree, and there's absolutely nothing wrong. And yet there's a certain stigma in parts of academia where everybody needs to go on, get a PhD, and go back into the academy. And I just think that's totally wrong. And I think we need to have more of an emphasis on, and that means then on the private sector, more opportunities for internship and training of graduate students. I go back to that example I mentioned with Neil Jacobs. I thought that was great for other students. It was great for Panasonic. We need more of that so that, you know, our students know that there are avenues for gainful employment post-degree, and it doesn't have to be just a PhD.
Good morning. Nevermind from Lyles. So I'm going to stick to this chart because I was part of the strategic sciences working group that was part of the Deepwater Horizon. And I like your comment because about the fact that this is likely one of the first times where science was properly used in a time of crisis. At the time, Marshall McNaught, who was heading USGS, with Gary Mathis, who was reporting to Ken Salazar, formed a crisis center dedicated with science, because there's a tendency for these situation rooms full of emergency managers do not have scientists involved, and they were scratching their heads when this was happening. And so, perfect. So at the time, they adopted a system ecology approach to dealing with this, which led to then the Gulf program. But that involved ecologists, involved things that your FEMA folks would never. And so I think, what do you think is the future there as we see these more recurrent disasters where scientists are heard and listened to?
So thanks very much. A couple of things. Again, the federal government response to Deep Horizon was great. However, I'm going to stress again, that was after the fact. Up front, if somebody wanted to propose something within NOAA, other agencies, that cut across every line organization, it was dead on arrival, right? The system was not set up to do research that way. So we need to set up system to do research that's truly transdisciplinary, not just a physical climate. So that's one, all right? Then the other thing, that's why I put this up, when I talk about modeling the human system, it need not be a deterministic numerical model. It could be this what's on the right could be very much what you described, more like a tabletop exercise or war game, the equivalent of war gaming, to probe what are the different avenues of human responses. But we need to make that integral to our modeling systems. All right, so I think we need more research. Again, behind the curtain, the intelligence community does these sorts of things, and we need to draw on that into our modeling of the Earth system to look at what are the avenues for responses. And right now, it's very, I can't even say it that hot. It's really not happening, and it needs to happen. Yep.
As a follow-on, I just wanted to say that when the Deepwater Horizon case, there was some ocean modeling experiments coming out of University of Chicago, St. Oxford, and they said that the Gulf Stream, the oil would get into the Gulf Stream, and so there was some doomsday scenario results. However, it turns out that the microbes that are below, like a couple miles below, they were eating those oil things, and it did not come to pass, fortunately for all of us. So we did not get that oil spill into. So yeah, the Earth is big, full of magnificent surprises for us. Yeah, at that point I remember it's going to enter the Gulf Stream and land up there, then the AMOC, etc., etc. That didn't come to pass. Just highlights looking at the whole system. Well, if there are no further questions, let's give another round of applause. Thank you.
Thank you, everybody.